Transformations using DESMOS. Over here on the left-hand side, I have three functions. This middle one right here, this blue one, is going to be our parent function. The one underneath it in black you see is just a copy of it, and you can see how the graph is exactly the same. And f is just the name of the function. If I were to change that to h, it kind of gives me a little question mark here going, what do you mean by h? I don't know what h is because it's not defined, but f is defined. This one up here is just showing the equation equivalency. So when I turn that one on, you can see the orange matches this one exactly. So it's the same function. This one's an equation method, and this one's in function form. But f of x and y are exactly the same value. So we're going to come back and show how this looks after using the transformation down here at the bottom. Now I'm going to add a k value. And it doesn't know what the k is, so I have to add the slider. And now the slider is set to 0, so it hasn't moved. So now, if I were to move this over to the right, increasing the k value, you can see it's going up. It's sliding vertically up. So if I make this k value of 3, it's f of x plus 3. And all that changes is the vertex was 0, 0, and it now becomes 0, 3. So only the y value is changing. So it was 0, but now it's 0 plus 3, which changes to 3. If I switch this to -3, then it's the same thing as saying 0 here, minus 3 gives me a -3. If I turn the orange one back on, you can see it's still at the parent function, but I can make it look like the transformed one of f of x minus 3 by putting a minus 3 right here. Okay, so now I'm going to get rid of the k on the outside and put a minus h on the inside, minus h. And then of course it doesn't know what h is, so I have to add an h slider. And h starts at 0, so it still looks just like the parent function. They're exactly in the same spot. But if I slide that to the right, making h bigger, you can see how the whole graph actually moves to the right. So if I move this up to 4 and compare their vertices, you'll see the only thing that changed was the x value changed by adding 4, because it's inside the function adding 4. If I go back to my equation method, you can see it's still at the origin, which is the parent function. And if I were to put a minus 4 inside parentheses like this, you'll see it shifts to the right just the same as the black one did. But notice that it's got to be inside, subtracting from the x first before the power of 2 is done. That's what it looks like when it's in equation form. This is just general function form, could work for any function. Of course, I could slide this to the left 4, or I could even slide it to the left 5. And then I would change this to a, now if I change this to a 5, you'll notice it stays on the right. That's because this h value is a negative. And if I put a negative up in there, -5, it moves over. Now, we wouldn't normally see it written that way. We'd see it written as +5, because minus a negative makes a positive. So this ends up being in the same spot as the black one. Okay, so I've now added the h and the k in there at the same time, and I've reset these to 0. And I've also put 0 up here. So -0 here, and this should be a +0 on the outside. If I turn that function on, you see it matches the parent function and the transform function all the same. Now I'm going to take the h value and slide it to the right. Slide it to the right 4. And then I'll take the k value and slide it down 3. And you'll notice two things changed on the vertex. The x became 4, so 0 plus 4. And the y became -3, so 0 minus 3. If I turn the orange function on, I can make it match the same, but I have to put a 4 in for h, moves it to the right, and then a -3 in for k, so -3, and now my function matches exactly. Okay, so now we're going to look at dilations, which are stretches and compresses, and I'm going to add an a variable out in front, and I'm going to add an a slider, and the a defaults to 1, which means this thing hasn't changed. It's the same as the parent. If I increase this a value, you'll see that the graph becomes more narrow. That's a vertical stretching, making all the y values get further away from the x-axis. The only one that doesn't move is the vertex, and that's because we're timesing the y value by the a value. Over here it's 4, but 0 times 4 does not change its position, so it stays right there, but everything else gets 4 times bigger. So the dot that was here at 1, 1 is now up here at 1, 4. If I make this slider go less than 1, you'll see that the graph gets wider and wider, which is a vertical compression. It's making all the y values get smaller. So if I make this a half, each of the y values are getting half as big. So this negative 2, 4 becomes negative 2, 2 down here. And if I turn my orange function back on, you'll see it matches the parent function in the middle. And all I got to do is put a 0.5 out in front of this, so 0.5, and my orange function matches the same as the black transform function. Now we're going to switch to horizontal dilation. So I'm going to take my a value and move it to the inside with x. Normally this is a c inside there, but I already have the a slider built, so I'm going to leave it as is. Now when I move this to the right, make the a value bigger, you'll see that all the x coordinates are getting closer to the y value. So it's moving inwards, right to left on this side, and left to right on this side. It's pushing inwards. I'm going to make that a 2. And then I'm going to come up here, and if I put a 2 on the outside of my orange function, you'll see it doesn't quite match up exactly with the black one. And that's because the times 2 is inside with x. And this times 2 is not inside with x, therefore it's not being affected by the power of 2. So to make this look the same, we'd have to put parentheses around the 2 and the x, and now it looks exactly the same. Turn that one off. Now, of course, if I went down to numbers that were smaller than 1, let's say a half, the same thing is going to happen here, but instead of calling this a vertical compression, we call this a horizontal stretch. So it's pulling outwards, making all the x values get twice as big. And that means if I were up here on negative 2, 4, the horizontal stretch is going to make the negative 2 become twice as big. So negative 2 times 2 is going to be negative 4. So I'm going to move out to negative 4, negative 4, and 4. So they got 2 times further away from the y-axis. I can make the orange one look the same, but I would have to put a 0.5 inside, so 0.5, and now it looks exactly the same. If I were to put it outside the parentheses, you'll see it doesn't quite match up because it's not horizontal, it's actually a vertical compress. So the vertical compression isn't as pronounced as the horizontal stretch, only because of the quadratic part of the function. Okay, the last one is going to be reflections, and reflections are just multiplying with negative. So on this f of x, I'm going to put a negative sign. You'll see that it flips over vertically. So up here we had a 2, 4, and the only thing that's going to change, the y value is going to change to the opposite, so it's going to become 2, negative 4 down here. If I turn my orange one on, I can do the same thing by putting a negative on the outside. Now if I put a negative inside on x, you'll notice nothing changed, or at least it doesn't look like anything changed. And that's because the axis of symmetry is right here in the middle. So this point right here reflects over to here, and this point right here reflects back to this side, so you can't see anything. So the best way to show this reflection, let me turn this off, is to put one of those h values back in there, so minus h, and then I'm going to move this thing off center. So let's say I move it 3 units to the right, like that. And then if I put a negative inside, you'll see it reflects across the y-axis as expected. The same thing would happen up here to the orange one, but I would have to put an h value in there to move it off center, because if I put a negative inside parentheses here, you'll see nothing happens until I shift it off center. So this one was minus 3, so if I put minus 3 here, you'll see it does actually reflect. So I'll get rid of that negative, it's on the right side, put the negative back on, and it reflects to the left side. And then of course you could do any combination of these. So let me put this one back to the parent. Okay, so down here I've put this one in what's called vertex form, and the same thing up here in equation, because this is normally how we would see it, but you could see it written this way. And of course the h is causing a horizontal slide, so if I move this to the right, it shifts to the right. If I move it left, it shifts to the left. If I move this thing down or up, say I move it down, and then if I make my a value bigger or smaller, or I could put a negative on there and it makes it flip upside down. In fact, let's put a negative 2. Negative 1 would be right there. That's the normal curve that we see over on this side. But if I put a negative 2, it makes it two times steeper. So we got a much steeper graph over here. Now if I turn the orange one on, you'll see I put the a, the h, should be an h there, in the k value, the same values that are down here. This orange one should match this one exactly. So let's turn it on and see. Yes, it is exactly in the right spot.